Welcome in our day's class. And today, I want to look at set values. How do we get them? And the central limit theorem in statistics. Previously, we were able to calculate the mean of a given data set. And also, we were able to calculate the variance and the standard deviation of such a given data set. So I want us to go a step further and apply the mean we calculated and the standard deviation we calculated so that we can able to calculate the set values. And from the set values, we'll be able to see how we apply them in statistics. Very important that when you are calculating the the mean and the standard deviation, it was not the end. We, of course, used these descriptive statistics to describe how the data is spread from the center, which is the mean. But we can go further and come up with Z values from the mean and the median, from the mean and the standard deviation. And thereafter, we can be able to see how statisticians have used these values, Z values, in deriving the central limit theorem, and thereby even conducting robust research. Let us begin on how we get the set values from raw data. First of all, I'll begin at looking what are set values and how do we get them. In this section, as I said, you learn how to use the mean and the standard deviation to create the said scores. And also, you'll be able to scribe a score in terms of how much it's above or below the mean. And also, we'll hope to know how to make use of the mean and the standard deviation to describe a particular score. Specifically, a set score is the number of standard deviation. The actual score is above or below the mean. If the actual score is above the mean, then the set score is positive. And if the actual score is below the mean, then the set score we get is negative. Set scores have many practical uses, as I've said. They are usually useful for showing exactly where a particular score falls on the normal curve. The formula for us to calculate the set score is Z equals to raw score represented here by X minus the mean all over the standard deviation. Z score is given by X, which is representing the raw score minus the mean all over the standard deviation. And I've already said that X here means raw score, M here represents mean of the data given, and SD represents the standard deviation. Now we have the data we were using in our previous examples, is the data I want us to fall onto. And from this data, we are going to calculate the mean of this data. We see there are 10 values in this data set. And as such, when you add all the values in the data set, the sum is 190. Because you will see from this data, that when you add all these values, you add 10 plus 12 plus 14 plus 16 plus 18 plus 20 plus 22 plus 24 plus 26 plus 28. The sum will be 190. Now we proceed to calculate the mean of this data. Now the mean is going to be 190, which is here, divided by R10. And the mean is 19. The mean for this data is 19. And remember, we are moving on. We are going towards calculating the set scores of this data. So we move also and calculate the standard deviation of this data. And as I said in our previous class, that the standard deviation, you take the raw score minus the mean. In this case, you take 10 minus 19, and you'll be able to get -9. And then we square this -9, and you'll be able to get 81. Also, the second part is 12 minus 19. You get -7, and then you square -7. You get 49. Also, here we have 14 minus 19. We get -5. Then we square -5. We get 25. Also, we have 16 minus 19, and 19 is our mean. We are able to get -3. When we square -3, we are able to get 9. Then we have 18 minus 19. We have -1. And then when we're able to square -1, we get 1. We have 20 minus 19, 19 being our mean. Then when we square 1, we get 1. 22 minus 19, we're able to get 3. 3 squared is 9. 24 minus 19, you get 5. And when 5 is squared, we get 25. 26 minus 19, you get 7. You square 7, you get 49. Then we have 28 minus 19, you get 9. And when you square 9, you get 81. Now, you add all these numbers, 81 plus 49 plus 25 plus 9 plus 1 plus 1 plus 9 plus 25 plus 49 plus 81, you get 330. Now, in calculating now the standard deviation, you first of all have to start with calculating the variance. So the variance will be x as the summation of x minus mean squared. And this is what I'm having here, 330 all over the number in the sample size here, which is 10. So this will be 330 all over 10, you get 33. But this is not the standard deviation. We take now the root of variance to get the standard deviation. The root of variance in this case will be the root of 33, which will give us 5.745. This is now the standard deviation. We have calculated the standard deviation, and also we have calculated the mean. we have two things here. We have mean of these data sets, which equals to 19. And we have the standard deviation, which equals to 5.745. Remember, the Z score we are going to calculate equals to raw score minus the mean all over the standard deviation. This is now the formula. We want now to apply this for calculating the Z score for every raw score in this case. So we proceed and get the raw score. And in this case, the Z score in this case, we are going to fill in this column. So in this column, we are going to have the raw score, which is 10, minus the mean, which is 19, all over the standard deviation, which is, we found it was 5.745. 5.745. You should be having your calculator so that you fill for me these values here, so that you'll be able to move together. Then in this case, we are going to calculate the Z score here. It's going to be 12 minus 19 all over the standard deviation, which is 5.745. We get the value there from your calculator. Then here we have also 12, not 12, 14. 14 minus 19 all over 5.745. In this row, we have 16 minus 19 all over 5.745. With your calculator, I hope you are getting the values here. Then in this row, we have 18 minus 19. 19 being our mean, all over 5.745. Here we have 20 minus 19 all over 5.745. Hope you are feeling and you are moving together with me. Then here we have 22 minus 19 all over 5.745. We have also here 24 minus 19 all over 5.745. Just about to finish, equals to, have your calculator to calculate and see what you're able to get there. Then here we have 26 minus 19 all over our standard deviation, 5.745. You see what you're going to get there. And finally, we have 28 minus 19 all over 5.745. Good. Now, there's one thing you should have realized in your answer. You should have gotten these values. In your answers, you should have gotten these values. The first value is negative 1.56658. Second value is negative 1.2185. On the value, the z-score associated with the raw score of 14 is negative 0.87032. And the z-score associated with the raw score of 16 in this data is negative 0.52219. Then you go up to the raw score of 28. You are going to get 1.56658. Now, these are the z-scores associated with these raw scores in this data. How do we use these values? How do we apply them in statistics? But before we apply them in statistics, I want us to get some characteristics in these set scores. If we decided to get the mean of these set scores, all of them, we add all of them. We add all of them and get the summation here. And we divide by the number of the values that are present or are available in our data set. What do we see? So there are several things we see here. The mean of the distribution of the scores is always 0. The mean. If you are going to get the mean of these set scores, all of them, in any given data, if you have a data set and you are calculating the mean of the set scores you got, it will always be 0. This is because when you change each raw score to a set score, you take the raw score minus the mean, so that the mean is subtracted out of all the raw scores, making the overall mean to come out to be 0. In other words, in any distribution, the sum of the positive z-score must always be equal to the sum of the negative scores. And you have seen these are the negative z-scores, and these are the positive z-scores. So when you add the negative ones and you add the positive ones, the sum of these negative ones always equals to the sum of the positive ones. That's very important for us to note as we move on in this lecture. The second thing I want us to note is the standard deviation of the set scores. The standard deviation of any set score. So in this case, we are not calculating the mean of the raw scores, but we are calculating the mean of the set scores that we have calculated in this. In this case, we have, if we have to get the standard deviation of the set scores that we have, we only have to now get this value and square it. And as you can see from the answers here, what we have squared, I've given it in this row. I've given it for this value of negative 1.5658, it's 2.4542. I'm squaring it so that I'm able to get the variance of the set scores. So after squaring all of them up to the last one, the attend values, I've squared all of them so that I can be able to get the variance, squared all of them so that I'm able to get the variance. And what I'm getting here is the total score here is 10. The total score here is 10. And the variance for all these is 1. And when you get now the the standard deviation or the root of the variance always equals to the standard deviation. And in this case, the standard deviation is equals to 1. So, very important, the standard deviation of any distribution of set scores is always equals to 1. We have seen two things. The mean always equal to 0, and the standard deviation of any distribution of set scores is always equals to 1. Then, how do we apply these set scores? How do we apply these set scores? We apply the set scores in calculating the proportions in the normal curve and the percentages between the mean and the standard deviation. And as we said, you know, when you are defining our set scores at the beginning of the lecture, we did say that a set score is the number of standard deviation. The set score is the number of standard deviation the actual score is above or below the mean. So, and we have seen that the mean is 0. The mean of the standard scores, the mean of the set scores is 0. So on the left, we might have one standard deviation, and on the right also, we might have one standard deviation on the normal distribution curve and on the normal curve, as we have seen. So we are good. It's good. We are good to use these values in getting the distribution on a normal curve. Now, the shape of the normal curve is standard. Thus, we are saying that there is a known percentage of scores above or below any particular point. For example, exactly 50% of the scores in the normal curve are below the mean, and another 50% is above the mean or on the other side of the mean. And that's why we say that this distribution is symmetrical, because a half of the score fall either on below or above the mean. And as you can see in the diagram I'm having here, these are the sets, and this is my mean. So I have 1, 2, 3 standard deviation on above the mean, and these are -4, -2, -3 standard deviation above or below the mean. And because they are below the mean, that's why I'm using the negative parts. Now we move further and see now the distributions of percentages, the distribution of percentages in our normal curve using these set scores. So we say approximately 34% of the scores are always between the mean and one standard deviation. This is the area I'm talking about, that 4%. And I said it's either on either side of our normal curve. So 34% is of the scores are always between the mean and one standard deviation. And this is either on either side. So this on the above the mean or below the mean. So also, we will say that, as I said earlier, that set score is the number of standard deviation. Set score is a number of standard deviation that a score is above or below the mean, which is just what we are talking about here, for being one standard deviation below and one standard deviation above the mean. And as we proceed and as we move on, we will see that the other between one standard deviation and two standard deviation, we have approximately 14% of the score lying in that area. Between one standard deviation and two standard deviation, we have approximately 14% of the score lying in this area on either side, 14% on this side and 14% on the other side. Now, because the normal curve is a precise mathematical curve, you can figure the exact percentage of the scores between any 2 points on the normal curve, not just those that happen to be on the right or at 1 or 2 standard deviation from the mean. And we are saying approximately 13.13% of the data always will fall between the mean and 1 standard deviation above the mean, and the other one, 13.134, that 4.13%, sorry for that, 34.13% of the data will fall between the mean and the standard deviation below the mean. That's what I have been saying here. Now, let us give more meaning to this. Let us give more meaning to this. Because the normal curve, we give more meaning to this by looking at another concept. And this concept, we call it the central limit theorem. The central limit theorem. Because it goes hand in hand with the set scores. We are trying, because the set scores are actually trying to bring us to the normal curve. But I want us to discuss now in detail about this central limit theorem. Now, what is it? The central limit theorem is a fundamental concept in statistics, and it states that the sampling distribution of the sample mean approaches a normal distribution as the sample size increases, regardless the shape of the population of the distribution. In simple terms, the central limit theorem tells us that if we make a multiple random sample from a population and calculate the mean of each sample, the shape of the sample means will tend to follow a normal, that is a bell-shaped distribution, the one we have seen earlier, even if the original population distribution was not normal. I need to explain in much details here, and I'm going to give an example. A researcher doing a research with students, and he wants to know their heights, their average height in a school, and it takes about a sample of 50. It takes a sample of 50. And from the 50, we don't know how the distribution of the height is. It might be skewed. That's why I'm saying now this makes this one becomes our population, not a sample. This one becomes our population. And in this population, it might be skewed. The height might be skewed. And the researcher now goes into this population and draws a sample. And let me say that he's drawing from this, a population of 50 is drawing a sample of let me say 6 individuals randomly, not purposively, randomly goes there and he picks 6 individuals from the 50. He measured their heights and record their heights, and he gets the average, or he gets the mean. So we say that this sample 1, we get the height of that sample 1, and we record the mean of that sample height. So we have 6 members, we measure their heights, then we record their heights, and then we get them in. Then we move on again. We get another sample from the same population, that's sample 2. 6 individuals again. We measure their heights, and then we calculate the mean again. That will be sample mean 1. That this will be sample mean 2. Then we go again randomly in the same population again. In the same population again. And then we get sample 3. We measure their heights. And then we get the mean of those heights. That is sample 3. We move on again to the same population. We get another sample again. In that very population, we get 6 individuals because we are using 6 individuals at every time. That's our sample. We measure their heights, and then we get the mean of those heights again. So this is mean 1, mean 2, mean 3, mean 4. We move again in that sample, and we move on until we get to the sample. We are going sample N, that very last sample, the finite sample we are able to get in that very population. Because we are doing randomly, it means that as we are doing that sampling, as we do the sampling, these individuals, we measure them, and then they go back in that population. Then we do this one up to that level. Then one thing we'll be doing, we will be taking now the frequency of this sample mean. We will be taking the frequency of this sample mean. How many times is this number appearing? And you will realize that when we now plot the frequencies of these sample means we have taken, we plot now on we take the frequency density and we plot. We will produce a normal curve. And that's why we said in our definition that the central limit theorem is whereby when we sample from a population, which is skewed or which is not normally distributed, and we get now the mean. As we now plot these means that we are plotted, that we got from the main population, will produce a normal distribution. They will produce a normal distribution. Sampling distribution of a sample mean approaches a normal distribution as the sample size increases. Now, there are several underlying factors that we must put in consideration as we do this. What are these fundamental we must put in place as we are doing this calculation? The first one is that we are doing random sampling. That everything, as we are sampling from the main population, the samples that are being selected are randomly selected from the population. We are not being biased that we go there and we say we will follow a criteria like purposive sampling. We say that these are the individuals we are going to measure their heights. No. Another fundamental point that we must take in place when we are defining central limit theorem is that our sample size must always be greater than or equal to 30. In other words, the sample size must be sufficiently larger. Anything that is less than 30 will not give us that central limit theorem, will not give us that normal curve. It assumes that we are typically using sample which is greater than 30, and the sample size should be greater than 30. Now, as the sample size increases, the sampling distribution of the sample mean becomes increasingly normal. The third fundamental point that we must be able to take in consideration when you are dealing with central limit theorem is the independency. The samples must be independent of each other. Each observation should not be influenced, or the selections of this observation should not be influenced. Every observation is independent of each other. Also, when you are using central limit theorem, we must be aware about the population variability. Now, the central limit theorem holds regardless of the population of the shape distribution, as long as the population variance is finite. Very important that you keep these 4 points in mind when you are using central limit theorem. In summary, the central limit theorem provides a powerful tool for making statistical inferences by allowing us to approximate the distribution of a sample mean or sums with a normal distribution, facilitating hypothesis testing, confidence intervals, and other statistical analysis. What is the relationship between Z values and central limit theorem? The relationship between the two lies in their shared application in statistical inferences and standardization of data. Z-scores and central limit theorem are closely related in the application to statistical inferences and standardization of data. The central limit theorem enables the use of normal distribution-based method, while the Z-scores also allow for the standardization of the data and facilitate comparison within the context of the standard normal distribution. I've talked about standardization with the Z-scores. When we use the Z-scores, actually, we use them to standardize data by expressing individual data points in terms of a standard deviation from the mean. The way we began our lecture by showing how we calculate our Z-scores from the raw data by using the mean, by subtracting the mean from every score and dividing the scores and dividing whatever we get by the standard deviation. This standardization allows for comparison across different distributions and facilitate hypothesis testing and confidence interval estimation, as we will see at the end of the lecture. And also, the central limit theorem states that the sum or average of a large number of independent, identical distributed random variables approaches a normal distribution, regardless of the original distribution of the variable. This property of the central limit theorem is fundamental in statistics, as it allows for the use of normal distribution-based method in a wide range of scenarios. Confidence intervals. I've talked about confidence intervals when I was talking about the Z-scores. Now, in a standard normal distribution, approximately statisticians have calculated and have come up with normal distribution tables, and they approximately say that 95% of the data falls within approximately 1.96 standard deviation of the mean. So we're saying that the said value corresponding approximately 95% of the data in a standard normal distribution are negative 1.96 and positive 1.96. Now, the 95% confidence level is commonly used in research because it provides a balance between the precision and reliability. However, researchers may choose a different value or a different confidence level depending on the study objectives, desired precision, and acceptable level of risk. For example, a researcher might decide to use 90% confidence interval, or the researcher might decide to use 90% confidence levels. Because what I'm saying, the study objectives, desired precision, and acceptable level of risks in the study a researcher is carrying out. The set value corresponding for that 99% of data in a standard normal distribution are a negative 2.576 and positive 2.576. Now here a 99% confidence interval in research is a range of values calculated from a sample that is believed to be 99% confidence to contain the true population parameter of interest. A 99% confidence interval is wider than 95% confidence intervals because it captures a larger proportion of distribution, providing greater confidence but less precision. Now, as I said earlier, researchers may choose different confidence levels based on the study objectives, desired precision, and the level of risk to be tolerated in the research. How do we determine the sample size? How do we determine the sample size? Now, when you go, as we have said, when you go for the research, you don't use the entire population. You use a sample, and this sample will be a true representation of this very population you are studying. So, determining the required sample size for a desired level of confidence involves several factors and consideration. And here is the general approach. The first approach, you define the parameters in your research. Start by specifying the parameters relevant to your study, such as population size, if finite, and the level of confidence you desire. And I've talked about either 95, 90, or 99. And also determine the margin of error you can tolerate and the variability of the population. Second, select the confidence levels. Choose the levels of confidence you want to achieve. And common choices, I've told you, we have either 90%, 95%, or 99%. Determine margin of error. Decide on the margin of error that you can tolerate. The margin of error is the maximum amount by which you are willing for your estimate to deviate from the true population parameter. Number 4, estimate the population variability. If you have prior knowledge of the population variability, use it to estimate the population standard deviation. If not, you may need to conduct a pilot study or use a conservative estimate. Number 5, proceed now to calculate the sample size and use a formula or a statistical software to calculate the required sample size. And when you are calculating the sample size, you are using the set scores at that very confident level you have chosen and the margin error that you have decided in your research. Then number 6, adjust for finite population if necessary, not a necessary step, but you can adjust. If your population is finite, not very large compared to the sample size, adjust the sample size formula using the finite population correction factors. Some of these things we look at them in advanced statistics. Then finally consider the practical constraints. These practical constraints include time, cost, and resources when determining the final sample size. I have a question here, which I want us to go through as we come to the end of this lecture. Suppose you have conducted a study involving a sample size of 150 students. You collected their test scores on a standardized exam and found that the sample mean test score is 50 with a standard deviation of 20. You need to calculate a 95% confidence interval for the population mean test score using the normal distribution and the set scores. Now, determine the confidence interval. How do we proceed in answering this question? First, you have to look for what you have been given. You have been given the sample size, n, which is 250. You have been given the sample mean, which is 50. You have been given the standard deviation, which is equal to 20. And you have been given the confidence level, which is 95%. Then, how do you proceed to answer that question? The step number 1, determine the critical Z value. Step 1, determine the critical Z value. Since we are using a 95% confidence level, we need to find the Z value that corresponds to the middle of 95% of the standard normal distribution. Now, the critical Z value for 95% confidence level can be found using the standard normal distribution table, or it can be calculated. And when we are using the table, these tables only give one value. But these values, we should remember that is a two-tailed test. It's either on the right side or the left side. So when you look at this value, we are supposed to know that the normal distribution has either those values that fall on the left side and those values that fall on the right side. And in this case, when you're using the table like the one I'm going to show you, this table here, we are going to look at one we're going to look at these values, the Z values. You see, you have been given the Z values on this side. You have the Z values on this side. And on this side, we have the margin of error. So we're going to look at 1.6. What are the values corresponding at margin error of 0.05? You find that it's 0.9505. And this value here corresponds, and actually this should be the value here, because or our value is 95%. 95%. 95% is this value here, 0.95. So when you multiply by 100, it will be 95% here. And this one is at margin of error 0.05. So this is the value that corresponds to that. And when now you are calculating, you are going to get E equals to Z plus. This is step number 2, because the first step here, we were looking at a Z value at 95%. We found that it's 1.96. And the second step is to calculate the margin of error. And the margin of error, we use this formula. Margin of error equals to Z plus Z value plus the standard deviation all over the root of the sample size. And the set value that corresponds to 95% confidence level is 1.96. So this one we will put there. And our standard deviation was 20. So we'll substitute here 20. And our sample mean was 150. These are the values we are getting. They are here. We were given. So after substituting, you will find that your value, you are going to get your margin of error is 3 point. Your margin of error is 3.19872. Then you are going to look for the confidence intervals, and confidence intervals equals to sample mean minus margin of error, or sample mean plus margin of error. So the sample mean was 50, and the margin of error we have calculated is 3.19872, and also it's 50 plus the margin of error we have calculated 3.19872. So the first answer we have gotten is 46.8128, and the second one is 53. So these two of them, we put them together with we separate them with a comma there, and then we say, therefore, the 95% confidence interval for the population mean test score is approximately 46.80, 53.0. Thank you very much. I'll make sure that we have a live class so that we can be able to explain some of the things you didn't understand in our day's class. Thank you very much.